using Henry's law to calculate the solubility of a gas. So Henry's law is that the solubility of a gas is the Henry's law constant Kh times the partial pressure of the gas. So in terms of units, etc., the Henry's law constant is usually in atmospheres of molarity per atmosphere. And if our partial pressure of our gas is in atmospheres as well, the units of our solubility of gas, atmospheres is going to cancel out. Solubility of gas is going to be in molarity. And remember, molarity is moles per liter. So it's all very well and good being, oh, I can just substitute, plug and chug in this equation, but you've got to understand what is coming out. So if I put my value straight into this equation for the Henry's law constant, 25 degrees Celsius is not a number you need to use, but Henry's law constant is temperature dependent. You probably already know this, but gases dissolve better in liquid solvents at lower temperature. That's why refrigerated soda is fizzier than warm soda, right? So it is temperature dependent. Okay, same as if water gets too hot for fish. If you're an aquariumist, is that word? Your oxygen level can decrease, right? You sometimes see that in the summer, lakes and stuff to get too hot, you get fish die off. Anywho, I digress. So basically, we can plug and chug this, but we are going to get our concentration of carbon dioxide given to us in moles per litre, and we are asked for the mass in grams of carbon dioxide. So the second part of that question is something you already know how to do from Gen Chem, which is take a concentration in moles per litre, molarity, use the actual volume to calculate the number of moles, and then use the molar mass of your substance to go from moles to mass in grams. So let's do some gathering of the equivalencies that we're going to need. We need to know that 1 milliliter is 10 to the power of minus 3 liters. And we need to know the molar mass of carbon dioxide. So carbon dioxide is 1 carbon, so CO2. So carbon is 12.011 grams per mole, as much as I can remember off the top of my head, and oxygen is 2 times 15.9994, I think, grams per mole. So that's going to give me a molar mass of about 44.0009. It's good enough. Grams per mole for the carbon dioxide. Okay, so let's just keep that up there somewhere. So in terms of equivalency, for every 1 mole of CO2, that is exactly 44.0009 grams. Okay, I like to write these as equivalencies because I just think it is easier to then put that into our calculations. All right, so my S gas is going to be my Henry's law constant for carbon dioxide, which was, where is it, 0.031 molarity per atmosphere. And my partial pressure, my carbon dioxide at 25 degrees Celsius was 2.61 atmospheres. So I'm just going to stick that in my calculator. Dimensional analysis tells me my units are going to come out in molarity. So that comes to 0.08091 molarity, which is the same as 0.08091 moles per litre. So for my unit conversion, I'm going to take that and just write moles per litre to make it easier to see. So I'm going to convert from moles to litre to moles. So what I'm going to need to do is actually multiply by my actual volume, which is 1500 milliliters. And this is where we have a little problem because liters and milliliters is not going to cancel. So what I need to do is calculate milliliters to liters. So I'm just going to do that conversion. You could do this on a separate line, but the way I like to teach it in class is to just put in that equivalency as a unit conversion, because then you can see what you're doing as you're doing it. So right now I can see my liters is going to cancel, my milliliters is going to cancel. Right now, if I press equals on my calculator, I have got the amount of carbon dioxide in moles. So in order to get rid of the moles, I'm going to take the mole mass as my conversion factor to convert between moles and mass in grams. So I want my 1 mole of carbon dioxide on the bottom and my 44.0009 grams on the top. So I've just taken that equivalency that I have up here, these equivalencies, put it just this equals that, and then you can take it and turn it into a unit conversion, like this one here, and then this one, okay? So now we can see in our unit conversion for our solubility of our gas, we've converted from moles per liter into just moles, and then from moles into mass in grams. So if I stick all that in my calculator, I end up with, hang on a second, 0.121365 moles. Sorry, I've got to keep going. So grams, that'd be 5.34115 grams. Obviously, I'm going to need to get it to the right number of sig figs, which is 2 significant digits. So in this case, that'd be 5.3 grams. Okay, so possible differences on this kind of question. I would look for things like the units of the volume of our solvent and things like the mass in grams versus mass in milligrams, etc. Milligrams is probably going to be quite common because gases are not typically hugely soluble in water, but you basically be following the same kind of steps. So that's grams, milliliters, grams, milliliters. Oh, not much variation there. Grams, milliliters. Okay, maybe I got too excited because this all seems to be grams and milliliters. That would just be my luck. So maybe there isn't going to be much variation when you guys are doing this. Okay. All right. Well, I'll leave it there then. Looking for my white whale, didn't find it. All right. Hopefully that's helpful.